are mostly associated with attracting rainfall owing to their ability to absorb water through their roots from the soil, which they use to prepare what is needed for their growth. They then release moisture through their leaves in a process better known as transpiration. The water vapor then rises to form clouds, from which we get the rainfall. However, when deforestation occurs, it leads to a lack of rainfall and drought, leaving rivers, wells and springs dry. But have you ever wondered how rain forms in the northern parts of Kenya, where trees are scarce and the vegetation is mostly shrubs? To unravel this mystery, meteorological experts are studying a powerful wind known as the Turkana low-level jet.
What we did was to try and have observations, an intense observation mission, where we are doing observations every 3 hours. Every 3 hours for about 30 days. That gave us a very good profile of what happens through the day. And that's why we managed to know when the wind is at its peak, when it is weakest, and how it is moving around.
This wind is linked to widespread low-level divergence across East Africa and is associated with relatively low equatorial rainfall in Kenya. Studies by the Kenya Meteorological Department, supported by independent research, also show that the Turkana low-level jet influences both flooding and drought.
The rift jet is a very strong, powerful wind that transports moisture from the Indian Ocean through Kenya, and it goes all the way to Ethiopia and the northern parts of Africa.
Climate scientists have now mapped the way this water vapor moves across the subcontinent. They describe it as flowing through the atmosphere like floating invisible rivers about 500 meters above the land surface, transporting 5 times the amount of water as that in the Congo River system. According to Professor Gilbert Ouma, senior lecturer at the University of Nairobi Institute for Climate Change and Adaptation and Department of Meteorology, the jet flows north through the counties of Garissa, Wajir, Marsabit and Turkana. The jet is responsible for approximately a third of water vapor transported from the Indian Ocean across the East African rift system to the continental interior.
You need moisture for rainfall. And if you look at the Turkana, the eastern part of Kenya, there's hardly any source of moisture. There's Lake Turkana, but it's a little bit to the north. So this mass of air with moisture in it can give us a lot of rainfall. So you need to keep observing it throughout. If it's going down, it's moving from the continents, the dry land coming down. There's no moisture in it, so we can't get rainfall from it. If it's going up, it's picking moisture from the Indian Ocean, gives a lot of rainfall, especially in the Ethiopian highlands.
But how exactly is the jet formed? According to Professor Ouma, the northern hemisphere has more land than water, and the southern hemisphere has more water than land.
Land and water heat differently. All right? One heats faster than the other. So when the sun is on the north, the land surface would heat a lot faster, and therefore you'll have an imbalance. There'll be more higher temperatures in the north, lower temperatures in the south. That creates a wind system. This is what's driving that jet.
He adds that when the sun comes to the south, the movement changes.
During the rainy season, it's moving to the north, brings moisture from the Indian Ocean. Then during the dry periods, December, January, February, June, July, August, it may be going to the south. But it is always there. Directions are the ones that are changing. So you need to keep observing it throughout.
The Turkana low-level jet was first identified in the 1980s by Joseph Hiri Kinuthia, a Kenya Meteorological Department officer based in Nairobi. His observations using pilot weather balloons revealed the existence of a strong southeasterly low-level jet in the Turkana Channel, which separates the Ethiopian highlands from the East African highlands. The study showed the jet existed throughout the year, with speeds exceeding 30 meters per second on a number of occasions and sometimes exceeding 50 meters per second. Observation then revealed the morning winds are stronger than afternoon winds. Professor Ouma notes that while these pioneering observations confirm the presence of the jet, they do not reveal the full diurnal cycle, quantify jet-related water vapor fluxes, or document the thermodynamic environment associated with jet formation.
The problems that were there were not major, but it is good to have a really good picture of what is happening as it's happening. So it's not like we are throwing away that paper, no, we are building up on that paper.
Modern reanalysis datasets often disagree on the strength of the jet winds and tend to underestimate the jet strength by 25 to 75% compared to the pilot balloon data.
This is a very important information for the area, the Turkana, Marsabit, that dry land piece. We know that they have floods. Sometimes those floods come from very heavy rainfall within that region. A lot of times it comes from Mount Elgon, where the source of the rivers are. But can we be able to focus these intense rainfalls for this region so that it can be used? This mission would give us that kind of data to be able to see when we are going to have the rains falling. We need that upper air information to be able to do that kind of forecasting. So the rift jet was very important in the sense that it could help us in planning for the water usage within these dry areas, the dry lands.
To reconcile these findings, the radio sonde investigation for the Turkana jet was launched from 26th March to 23rd April 2021, marking the first time in 40 years that the Turkana jet was measured using modern technologies. Forecasting these intense rainfalls will aid in water harvesting, disaster preparedness and drought mitigation. Moreover, during windy periods, the country can capitalize on the efficiency of clean energy from wind power. For Voice of Nature, I'm David Kagina.